we just consider a few problems and try to solve Navier-Stokes equation for those problems that were given in two-dimensional motion in rectangular and cylindrical polar coordinates. As I said earlier, the general solution is difficult to solve for non-Navier-Stokes equation. Only a few solutions are available under certain conditions. We call them as to find out the exact solution. Some of them are available, but specific conditions apply on them, and they are only available under certain conditions. So we consider a few of them by considering certain examples one by one, and let us look at them. And also we must see what are the other considerations which we should make note of before starting to solve the equations. For exact solution, there are few steps that we need to take, few conditions that we need to apply. So these are listed here for your convenience, and so that we also know and remember them, that we don't ignore any of these things, because otherwise we can make mistake and determine a false solution. So one of the steps that we need to take is the problem and its geometry. You may have observed that every now and then I talk about the geometry of the fluid problem or the fluid flow motion. Always make a sketch if you can. Try to keep the geometry in mind and try to consider the relevant coordinate system for that geometry and the problem. And also, of course, we need to know the properties of the fluid or the fluid that is under consideration, whether it is air or liquid, oil or what, viscous, inviscid, and so on. List all approximate assumptions, approximations, simplifications, and boundary conditions. They are so important, and they are also important because of the behavior of the fluid and because of the laws of physics that apply. The Navier-Stokes equation, as you know, have been derived on the basis of Newton's laws of motion, provided we are considering Newtonian fluids. So in those conditions, the physical conditions are very important. For example, if a viscous fluid is being considered, then the viscous fluid, if it is sticking to a surface, then what happens to the velocity? How does the pressure changes? How does the fluid behave? We need to keep that in mind. And the velocity of the two boundaries. What happens to the fluid at the boundary? It's so important. So, for example, if the fluid flow is taking in a pipe, in a channel, then at the radius of the boundary, that is at the boundary of the pipe, for example, how does the fluid behave? Does it move? Does it show a velocity? Does it rotate? If we are rotating the pipe, then of course the fluid inside will be rotating. But what about the fluid that is at the center of or that is at the axis of the cylinder, or the fluid that is touching the boundary of the cylinder? What happens to that? And it's so important that we keep that in mind. Then we simplify the differential equations of motion, that is the Navier-Stokes equation, as much as we can for our convenience, so that we can solve it mathematically. Since these are differential equations, we integrate them to find the solution. While finding the solution, by integrating, we will also determine the constants that are involved. We apply the boundary conditions to determine the constants. We verify our results by whatever means are available to us. Particularly, it will be very nice and useful if we can verify them by carrying out experiments and see that the same thing happens. Some of the boundary conditions that apply is that when the fluid is motion at a boundary, then the fluid away from the wall or at the wall, the velocities of the fluid must be equal to the velocity of the wall. For example, imagine there is an open channel flow, and let us say the water is flowing through a riverbed or canal. Then the boundaries within which the fluid is moving, then at the boundary, the water cannot flow because the boundary, the wall of the canal in which the water is flowing is stationary, is standing still. So the velocity of the water that is touching the wall of the canal will have a zero velocity. So that is the boundary condition. If the wall is not moving, the fluid should not also move. That is law of physics, and we need to apply. And that comes under boundary condition. Or I gave you the other method. If a boundary is rotating, for example, or moving, then the fluid that is in contact with the boundary of the pipe, for example, which is rotating, should have the same velocity that is of the pipe that is rotating. And similarly, there are other simple considerations, and they all fall under the category of the boundary conditions. We must apply them and ensure that the boundary conditions have been taken care of and they are applied while trying to determine the constants that occur as a result of integrating the differential equations. Again, at the interface of the boundaries, if there are two types of fluids that are meeting, for example, this is fluid A, this is fluid B. This can be water and this can be air, or some other two different kind of liquids, let us say, whatever. The boundary conditions remain the same. So at the joint of the two boundaries, the velocity should be equal. As we said before, these are the laws of physics that must be followed. If they are not followed, our solutions will be false. The surface forces, the stress, strain, etc., they have to be equal as well at both the surfaces. So the two values should be the same. Likewise, the same condition, the rules of physics must be followed, particularly in the boundary condition that I have mentioned, and also the surface condition with respect to stress and strain forces which may occur when the two different fluids are meeting or the boundaries are in contact at certain points. These are very important considerations while trying to solve the problem. And this picture also is trying to show the same thing, that we need to consider them.